my words very brief. Professor Satish Dhawan Visiting is currently here as the Satish Dhawan Visiting Professor for the year 2004-2005. Not that he'll be here the whole year, but he's here for an extended period of time. 24-25. But he's here now for about 2 years. He holds position as a university professor at New York University with affiliations in physics, mathematics, and engineering. This comes after a period as president of Brooklyn Polytechnic and dean of engineering at New York University. And over the previous decade, he led a major transformation where these two universities were brought together. Very complex task. As you can imagine, those who have been in administration can imagine better the many things that would have had to be done, many people who you have had to work with. But I understand this has had very good outcomes for the disciplines, for the people in the disciplines, as well as the quality of enrollment. Now, over the years, he has made many outstanding contributions, and I imagine some of what he speaks about today is on the basis of those scientific contributions. But he has also had provided leadership to the scientific community over many years in many ways, which has had broad impact on a large number of people. In addition to, let's say, the work at New York University. Before that, he was the director of the International Center for Theoretical Physics at IISc. I understand that when he went there was a revitalized program that saw scientists, about 6,000 scientists annually visiting that center, and a new program on Earth system physics. So, in my mind, I see that as a different kind of tide that lifts a lot of boats. I do want to, just for completeness, I would like to say that for his work, he has been recognized by being elected as a fellow of many leading academies. But more than that, in these academies, he has held many leadership roles as well. For this lecture, I will mention only a few of the most recent awards that he has received. The 2020 G.I. Taylor Medal of the Society of Engineering Science, the 2020 von Braun Medal of the IISc, 2020 Fulbright Prize of the American Physical Society, the 2022 Leo Kardanoff Prize of the American Physical Society, and the 2022 ASME Medal. The first time I saw him speak was when I was a graduate student, and from then itself I had the impression that he seeks a comprehensive understanding of the subject, and he brings new tools to bear on this to get that understanding, perhaps developing them himself, and yet there is something that remains.
Thank you, Joseph, for your generous introduction. I greatly appreciate the hospitality of the Institute, its director and his colleagues and the staff for making my stay here possible in the first place. I would like to thank the Aerospace Department, especially you, Joseph, for all the hospitality that you have given me. I also wish to thank a number of colleagues in aerospace department and in the physics department, with whom I've had many interesting conversations. Without these interactions, my stay would be really not making sense at all. I've been a frequent visitor to the Institute since I left 50 years ago, believe it or not. So I come here many times, but it's been some 30 odd years since I stayed here for any length of time like now. The Institute has changed over these years a great deal, many of them for the better. What has remained unchanged is how helpful it has been to me, particularly in help towards things that are big and small. So I'm very grateful for that. I'm very grateful for this occasion to be able to talk about this topic. I meant it to be relatively broad, but when it gets a little technical, if some of you think it is not accessible, please excuse me for that. So let me see if I can find something. Okay, very good. As I have advertised here, it's about what the turbulence problem is and when one might regard it as solved. I must confess that this talk is partly a repeat of the one I gave at ICTS last December. So if some of you are there, you will hear not everything the same, but some of the same things, so you should excuse me for that. So I begin with this quote. Turbulence is the last or great unsolved problem in classical physics. It's been attributed to Dick Feynman, apparently without any basis, because I and a few others have looked at Feynman literature corresponding to fluid dynamics, but nowhere do you see the exact statement. There are somewhat similar statements, but not this one. But anyhow, it's a nice quote. And if you go to any lecture on turbulence, general ones, people start with this thing, which, as I say, is not really attributable to Feynman. But I'm not going to take issues with Feynman. But the problem is, this has a lot of implications. This statement has a lot of implications for many people. They think turbulence has not been solved, whatever it means, let's say. Of course, I would agree with everybody that it is not solved, but I don't know what it means. Because it's not a very simple thing to define what that is. And it's not only turbulence in classical physics that has not been solved, but there are a number of others. For example, fracture, let's say high-density plasmas, or if you take, let's say, the structure of flow in the sun, and things like that. But turbulence is a little different because it is very pervasive. What I mean by pervasive is that if you are, let's say, a geophysicist interested in geodynamo, that is the dynamo of the Earth, which is shown here, it would not be possible without turbulence. It's interaction between turbulence and the magnetic field. Similarly, if you're an astrophysicist, planet formation from cosmic dust would not be possible without turbulence. It's the interaction between turbulence and particles that does it. If you're an engineer, these gas turbine engines, which are so impressive and so difficult to model, you would not do it or be able to do it without knowing about turbulence. But these are all very complex in the sense there is magnetic field here, the particles here, there's of course
could be high temperature effects, including chemical reactions and all that. So I will not talk about all of them. They are really very difficult problems. One that each of them really each of them requires many hours of discussion. But I will consider only turbulence of simple fluids without these extra things like magnetic fields and high temperature effects, etc. It's often called hydrodynamic turbulence, although many people who don't like the word hydrodynamics. That's a fluid turbulence, if you want it that way, in 3 dimensions. But you may think I have restricted too much, but it is not true. The scope is sufficiently focused, but not unduly restricted. It's a core ingredient of what you find in all these things. And it's of interest to mathematicians, physicists, and engineers alike. So it's a big subject. So what is it that I will do? It's special status as a subject in complexity. Maybe I should say what I mean. What is the special status in many complex fields? For example, the one I just mentioned, let's take a high density plasma, for instance. We don't really know what equations we must solve, but in this hydrodynamic turbulence, we think we know the equations to solve. And unlike many other many-body problems which have same complex behavior, this has this status that we know the equations, and in principle you can solve them on a computer as accurately as you want, although I will mention that later on what the difficulties are. Now, even if I restrict to hydrodynamic turbulence, there is an immense variety of problems. You may want to know what the distribution of the velocity is on a turbulent boundary layer. You might be interested in the University of small scales, that is fine scales which are far away from where you generate it. So all the generation mechanisms are forgotten. And you might be interested in things like uniqueness of Navier-Stokes and things like that. Now, even if you solve one of them, let's say, I don't know, pick one, if only a fraction of people will take notice. For example, you solve the problem of uniqueness of Navier-Stokes. It will not have a huge impact on many others. So in fact, we might ask, what's the heart of the problem? If you find the answer for that, everyone will immediately be excited. That's a question that I've been wrestling with for so long. Unfortunately, the answer is not that simple. I can give you problems in different areas that might be exciting, but one that excites everybody would be hard to say. My view is that this subject is a collection of a number of interconnected problems, all of which are important in their own right. There's a danger that if you don't recognize it, the field becomes fragmented, as it sometimes seems. And in fact, when you fragment a field, its advancement becomes muted. So let's say, for example, if you put at the center the turbulence, if you are a mathematician, you might be interested in the regularity problems. But then if you are a physicist, you might be interested in, let's say, anomalous exponents and things like that. If you are an engineer, you might be interested in CFD and how to compute flows and so on. So I have sort of tried to grade them in some way with intermediate problems that might be of interest to both the communities. But generally what happens is, let's say you have here anomalous scaling. It might really not have a great impact on issues like such as regularity. Or people in this community might simply not take notice of what's happening here. Now, that's really not so great a situation. And in fact, I think one must really have a good understanding of all of them. even though you might not be great experts, in order to be able to advance the field as a whole. I will only attempt to discuss a few of the problems like that, but I will try not to be too parochial. That is to say, I will not try to be saying only things in which I am practically interested. Now, the first question I want to ask is, I already put in the previous slide Navier-Stokes turbulence in the middle of that circle. By that I had the thought that turbulence is the same as the Navier-Stokes problem. That is to say, if that's turbulence, turbulent jets, so the screen is not wide somehow, it's really scrunching everything, but okay, let's move on. So let's say that's a turbulent flow, and of course that is the Navier-Stokes equations. U here is solenoidal velocity, and so here is the viscosity and here is the pressure. So let's say simple-mindedly the pressure drives the flow and viscosity slows it down, and this is the field, velocity field that arises as inertia. What we are interested in is the result of solving these equations when the viscosity is small, which is the same thing as very high Reynolds numbers. This is the one we are interested in. Reynolds number, as you remember, is the velocity times length divided by viscosity. So small viscosity leads you to high Reynolds number, which is what we are interested in. The question I asked in this title is whether the two are equivalent in most circumstances. Let's say we have extremely high Reynolds number. Does the flow that you might create in a laboratory and this, for instance, are they the same? There are other reasons to believe that there could be a problem there. This question has been asked very often. I give you a reference here, and they say yes, they are equivalent. The conclusion is mostly based on this fact that the smallest scale in turbulence is much larger than the mean free path at the molecular level. So that means the assumption of continuum works very well for the fluid, and you can say velocity at a point, which really is a point that is small enough, I mean the space is small enough to be regarded as a point, but it still contains many, many molecules. Now, of course, you can modify that work of 1959, probably before, first by showing that this small scale velocity is smaller than what people thought. So let's call that eta min. And it's also possible that if you have something like high temperature, you would have to modify some other things in these calculations. So the ratio here, the minimum distance, minimum scale in the flow, divided the mean free path, it goes like Reynolds number to the power m. M is unknown, and therefore I can't say too much, but we are interested, as I said, in the limit of very high Reynolds numbers, which is really what you find in many instances. In the atmosphere, for instance, the Reynolds number is very large, as in the ocean and the sun and all that kind of thing. So we should be interested in very high Reynolds numbers. I don't know M, so I can't be sure, but there are circumstances in which M could be of the right sign, so that the scale, the actual scale in turbulence could become comparable to the mean free path. In which case, you might wonder whether the notion of continuum, which is the basis of this equation, actually is applicable to turbulence. So if the Reynolds number is so large that the length scales are in the molecular range, the Navier-Stokes model for high Reynolds numbers has a problem. In fact, there are a number of people who say that the thermal fluctuations can determine what the turbulence measures are. In any case, there's a huge overlap between this equation here and what you see in things like that. So I'm going to proceed with the assumption that the two are the same, simply because I don't know better than that. So let's now start with the Navier-Stokes equations. One of the interesting things is that the Clay Mathematics Institute has established a number of millennium problems, some dozen of them or so. A few of them have been solved, and there's $1 million prize for solving one of these. And what's the problem they pose, the Mathematics Institute? And the problem is one of regularity. What it means is that in 3 space dimensions and time, given an initial velocity field, somehow you prove that there exists a vector velocity and a scalar pressure field, which are both smooth and globally defined. That is to say, they do not develop a singular behavior, for instance. When you say prove that, it might be that you can prove otherwise, which is also fine. And that's the problem. The problem is that the flow always remains smooth, so that you can actually measure things without any ambiguities, or solve the equations without any ambiguities. Now, in fact, it says here the equation which governs the flow of fluids such as water and air. However, there is no proof for the most basic questions one can ask. Do solutions exist, and are they unique? Why do you seek such a proof? Because the proof gives not only certitude, but also an understanding of what happens. So what will change if I prove the regularity problem of Navier-Stokes? Perhaps not for the most case, but it will have some impact on simulations, as I will describe in a minute. And but of course, for the endeavor to be successful, you have to have a finite bound in finite time, and long time averages must be calculable. So that's the thing. I said I will make a remark on the difficulties that might exist. We have some indications that there might be some difficulties. I say indications because it's simply not clear at all which way it goes. Now in 1972, Steve Arzog created a numerical solution of 3-dimensional homogeneous isotropic turbulence. He took a box which is periodic in all directions, and it was 32 by 32 by 32, and he put in that grid the Navier-Stokes equations, which are discretized, and solved them and found the various properties. 32 cube, just imagine. And now we are in the era, this was a paper last year presented at the American Physical Society, mostly led by P.K. Young, but you can also find my name here. And we can do 32,768 cube. Now just in 50 years, and it's a trillion-fold increase in computing power, a billion-fold increase in the computational domain. It's not very easy to find other tools in physics where such a huge increase has taken place, a billion-fold, let's say. Maybe synchrotron light sources have gone similarly. Now, the expectation was, and has been more or less, that if you can solve such a huge problem in a computer, it's a million-fold in Reynolds number, or 1,000-fold in microscale Reynolds number. So I might have thought, or I thought actually, that we would be able to solve everything, we would be able to answer everything, although of course it requires enormous computing power, and so far these are only experimental simulations. Nevertheless, the question has remained, but even in these experimental simulations, we can only achieve maybe 1/50th of the expectation that I have given here in terms of the Reynolds number. But why is that? Why is it that the standard expectations have fallen very short if 1/50 is a very significant number? So there are many technical reasons for that. The small scales keep becoming smaller and smaller, and you have to have finer and finer time scales and in order to have stability and things like that. But the question is it an indication that there are deeper problems? Because let's take something like 8,192, which is 1/4 of that. That's been calculated, of course, properly and for enough length of time and so on. But then it already shows, even if you resolve it well, there may be issues. And if the 3D Navier-Stokes equations do not possess strong solutions, that is, solutions that are applicable at all points and everything, we have only weak solutions, so-called weak solutions, which are solutions to the problem in an integral sense, for instance. And these are not unique. And if, in fact, the solutions to the Navier-Stokes equations are not unique, what does it mean for simulations as a fundamental basis for turbulence? Now, you will have to really think about it very hard. So, we may need new and better ways of numerical integration. That may be the problem why it is like that. Maybe we are being too dumb about how to do the simulations. Or it may be that you need to understand the regularity problem, and maybe the current methods one uses are not enough, and you have to go better. In any case, that's a kind of negative thing or pessimistic scenario. On the optimistic side, any new numerical methods could impact other methods people use, such as RANS, finite element methods, larger simulations, and statistically steady states. So we don't know where we are on this. The other thing I want to talk about is the vanishing viscosity limit of Navier-Stokes. I should explain what I mean by this. As I already said, we have the equations, we think we have, and we're interested in the behavior of that for very high Reynolds numbers or when the viscosity goes to 0. Now what happens when the viscosity goes to 0? If you put it equal to 0, you have either equations, that is, there is no viscosity. So we already knew in 18th century fluid mechanics, D'Alembert's paradox, is that the drag is 0. The drag is 0 if viscosity vanishes. And of course, that's a limit we are interested in. But our experience shows that the drag does not vanish. We know that. For example, here is a picture of the drag coefficient as a function of Reynolds number. You see here, it does go down with the Reynolds number, and somehow it stabilizes and then goes down and then comes up again and sort of stabilized. It's not going to 0 as the Reynolds number goes higher and higher. That is to say, as the viscosity goes smaller and smaller. So the D'Alembert's paradox, if it were true, would tell us that this will gradually go to 0, maybe not monotonically, but in some crazy fashion, go to 0, but it doesn't. Now there you have to understand what that is. You might say, well, you will have some singular-like structures and all this kind of stuff, but you have to know what it really means. Now, put it a little bit more technically, when viscosity vanishes, we might have thought that it would be like Euler, which is that everything is symmetric, but that's not true. Even as the viscosity vanishes, the symmetry breaking it does not cease. So you will always have a symmetry breaking, no matter how small the viscosity. That's a paradigm that we have to understand well. So even though the drag and so on and so forth viscosity is responsible for it, as long as it is there, however small it is, it produces the same effect in the flow. Now, a particular manifestation of this idea is the so-called dissipative anomaly. That is to say, the energy dissipation is finite even when the viscosity tends to zero. So you think energy gets dissipated in a flow because of viscosity, right? It's in fact, if you write down the expression, it's viscosity times the gradient squared, more or less. And now, when the viscosity goes to zero, you might think, well, the dissipation also goes down to zero, but it doesn't. And this is the so-called dissipative anomaly. And I wrote it down a little bit technically what it means. It means the gradients have to diverge. So I have a viscosity times the gradient squared. When the viscosity goes to zero, somehow the gradients have to go up in a way that balances the viscosity. This dissipative anomaly is a common basis for many other things, which I will not describe. So I called it the zeroth law of turbulence. I believe I am the one who coined this phrase first, but I'm not sure. Anyway, some of my friends give me credit for it, but not everybody does. So there is the zeroth law, which I want to explain a little bit. So here is Reynolds number. Reynolds number increasing means viscosity is going down. This is the energy dissipation, that is how much energy is being dissipated in a turbulent flow. As you can see, when the viscosity goes down this way, indeed the dissipation goes down for a while, but after that it remains constant. So somehow, for very high Reynolds numbers, instead of this continuing to go to zero, it sort of stays constant. Well, that is very interesting. And proving this one way or the other, of course an experiment doesn't prove things precisely. Maybe it will go like that and maybe begin to go further down, who knows. But proving this result mathematically would go a long way in establishing a theory of turbulence in a fundamental sense. So how were these data acquired? So there is a grid turbulence. So I have a grid of bars, and fluid is going from left to right, and there are a lot of little wakes, and they mix together to give you a homogeneous turbulence. And I might be looking at a region like that, which is far away from the grid, that the effects of the grid is forgotten, etc. And this is the picture I took from Naguib and Cork. So there are many other experimental studies after I produced this figure, by Kaneda, Danzis et al., in which my name is also there similarly here. They all show the same thing. But of course, that might not be quite true. There appears to be some recent revision of this in this paper that is taken about 5 years to write. I am an author as well. So it says maybe it will go to zero at a very slow rate, but the rate is so slow that actually many of the results that we know are carried through. Maybe, but we don't know that yet. So there are such kind of mathematical problems which think about turbulence as a solution of the Navier-Stokes equations, although the previous one is not exactly that. But if you are a physicist, you would not want to be hung up by the solutions of the Navier-Stokes themselves, because you're interested in the statistical behavior of the solutions. You're not necessarily interested on the turbulence as the PDE problem, that is the partial differential equations. which is the view that we took until now in my talk. It's not about individual solutions of the Navier-Stokes equations, but about their statistical behavior. Now, of course, then you will have to ask, what does it mean? Solving the problem of turbulence would require discovering what the right probability measure is and trying to obtain it somehow from the equations. Now, sort of that, knowledge of the specific solutions, of course, benefits the knowledge of statistical behavior, but the two are not identical. And the specific solutions to be useful, they shouldn't be so rare that they don't define for you the statistical behavior. But they must form a substantial set with respect to the relevant physical measure. The basic quest then is to characterize the robust statistical properties of high Reynolds number regimes. This does not exclude an understanding of the structure in the flow, or coherent structures or anything like that, but the statistical behaviors would include all of them. It means basically understanding which measures in function space, let's say, can arise in the limit of the Navier-Stokes equations. And then, what is our proof? What is our, let's say, evidence in the end that the statistical physics you invent is the right one? It is that they should satisfy the laws of turbulence. And what are those laws? We have to discover them. We basically have to discover, for example, the zeroth law or the dissipative anomaly. There are many other laws like that in which we think are true, but then there are always issues related to them, and I will try to describe a few of them. Before I do that, I have here a kind of caveats, and let's leave that alone. But there are many problems in statistical physics where your understanding has gone up by a combination of mathematical physics and numerical insights as well as experiments. And it's the case in turbulence that when only all of them go together hand in hand, do we understand what it is. It's not just an armchair discussion about what turbulence is, but one aspect trying to support what the other aspect has produced. So one result are the laws, the statistical laws we want to understand, which we think is true in a form I will tell you, is the celebrated results of Kolmogorov, 1941, many years ago now, 80 some odd years. And what it says is that this is the one result everybody knows, or most people here would know. It's, as I said, a celebrated result. And what it means is, if K is a wave number in the flow behavior, the energy associated with that wave number goes like wave number to the power minus 5/3. This is the famous 5/3 law. So let's see if that is true or not. And now, of course, before I show that, let me say that if in fact you compute the energy spectrum in terms of a single velocity field coming from the Navier-Stokes, then this has an implication on the regularity of the Navier-Stokes equations, which I will mention a little bit. You should construct a theory for this. So one problem in statistical physics would be to explain that. So is it true or not? So suppose I measure the spectrum of turbulence in a very high Reynolds number flow, in this case in the atmosphere. Here is the wave number. As you can see, there are several decades of the wave number. And here is the energy spectrum. And there is a wide range where you have a power law. This is a log law here. So this is a power law. And I want to know whether it is minus 5/3 or not. A better way to do it is take the spectrum and divide by the minus 5/3 power. So I should get a constant. You forget about this thing right now. So in fact, that's what I've done in this insert. And for very high wave numbers, it goes down, of course, until it hits the noise boundary of the experiment. So is this departure a little bit different slope from -5/3? Is it real, or is it just an artifact of, say, some experimental measurements? So is it looks like there is a departure, slight departure. Is that universal? That is, you take many flows under different ways of creating them, would you get the same result? And how would we obtain this constant here in front, which has a value, this is a logarithmic thing, approximately 0.5 or something like that. So how would one do that? So that's the problem. Let's say a typical problem if you want to solve it as a statistical problem. I plotted here this exponent from the experiments, from many experiments, as a function of Reynolds number. And this is what the Kolmogov's 5/3 would be. But experiments seem to show, I think you can say that overall there is an effect that is different from this. And this dashed line is the theory that Victor, Eckert, and I did. That seems to work very well. Here is for the fourth order statistics. This is the Kolmogorov line. And here is all the results, and this is the perhaps the mean result goes through the theory that we constructed. Now, so second order, you see this is a small difference. Fourth order, it's about 5% difference. But 5%, you may be wondering whether it is something that a theory should be built on or not. But if you go to high orders, they show bigger difference. If instead of fourth order, I go to say eighth order or something like that. And then there's some other quantities for which even very low order moments show zeroth order differences. That is to say, the theory says that it should be flat, whereas things just go up. So it's not dependent on little things like 5% or things like that. So as I said, let's look at one case where if you go to higher orders, what happens? If this is the order of the moment, and this is the exponent, this is what the Kolmogov's theory tells you. And you see they increase according to the theory more or less with a small difference, a few percent difference here, a few percent. But if you go to maybe 6th order, 8th order, it departs, not only does it depart from here, but it sort of saturates here. And this has very strong implications on what you think happens to turbulence. And this I will not take your time to describe right now. Another thing I mentioned already is you plot the Reynolds number here and you take the mean square acceleration of the fluid. So you sit at one point, you measure the acceleration and it fluctuates, and you take the mean square of that. Then instead of, the theory says it should be flat, independent of the Reynolds number. But in fact, it goes up. And we devised a theory again, dashed line. Never mind that. But the point is there are these deviations, and these deviations are real. And if you are creating a statistical theory, you should create one that accounts for these. We think this is all because there are huge fluctuations in the turbulent flow. If you take any stochastic process, just noise, for example, coming from some electronic device, let's say, it sort of varies, but it varies more or less like a Gaussian distribution. So it fluctuates very gently in some sense. Whereas if you take turbulence, the energy dissipation here, and I take a cut in the flow and plot how it behaves as a function of space, along a line, you can see that there are huge fluctuations once in a while, and there are small fluctuations and smaller fluctuations yet. Now this of course is very different from the standard Gaussian type statistical behavior, which I think is one type of situation. Now there, if it is a Gaussian, let's say you have a mean and you have a mean square, you have described the statistical behavior completely, because that's all the Gaussian has, the mean and the mean square. But here, if I give you the mean, well, it is buried somewhere here, and it doesn't really tell you much about these fluctuations. If I give you mean square, it will go up a little bit, but still it does not tell you much about it. So somehow or the other, you have to describe all these moments, all these complicated behavior, and this so-called multifractal description became very handy, and it basically decomposes such a signal into many sets for which you have a certain strength, let us say, and you ask yourself what is the dimension of that set, and you have an answer. So this is described a little bit here. And this was the work of many people the last many years. For the dissipative scales, it was Mandelbrot who talked about this without naming it multifractals. And Charles and I did much of the work. And for the inertial scales, it was Parisi and Frisch and many Italian colleagues of Parisi. And in dynamical systems, mostly it was Kadnoff and his colleagues in Chicago. So there are many people who can claim credit for this, as in fact one should mention. But the point is that a lot of work has gone on in this direction. But the problem that remains in some ways, aside from showing that the multifractal description is correct in principle, is that if I take a volume of a turbulence and I pick one little element there and I expand it here, the colors don't show up very well in this, but in fact the color code says that you are picking up this kind of huge fluctuations. And I take a little piece of that and expand it here, and it is shown here with a better color coding, but nevertheless, it is not just the magnitudes that actually fluctuate, but as you can see, they have a tendency to cluster. So intermittency is not simply the variation in, huge variation in amplitudes, but also this tendency to cluster. Surprisingly, as far as I can tell, there is not all that much work on it. Some years ago, we wrote a few papers, and one of them is shown here. But the point is, so intermittency is this clustering as well, and that really comes from the physical structure in the turbulent flow. You might call it coherent structures, large-scale things, whatever. But that somehow has not been integrated into this, as far as I know. So that's a problem that remains. So let's say we have these kind of problems under control for a turbulent flow. What is the general idea? Let's say I'm interested in a flow like this, which is the flow on the wall. From left to right, you have a boundary layer with these fluctuations here and a very complicated boundary. It's not clear what that is because the resolution is not good enough. Nevertheless, we know that this is a highly convoluted structure which may be described approximately by a fractal. Now, the traditional view is that if you are away from this boundary and away from the wall, so you pick some area like that there, it is just like what I described earlier, coming from homogeneous isotropic turbulence. So what it means is that the mixing is very large, as in homogeneous isotropic turbulence, and there is an enormous enhancement in dissipation and things like that. But what's the point? This is a homogeneous case and this is the real flow. The point is that if you take this small part, it may look like that. But in reality, if you want to describe such a flow in totality, you must know what the boundary conditions are, what the effect is, and also should know how these excursions matter. So that's the jump that one will have to make from the previous problems that I described to a real problem like that. Now, the main problem from the engineering perspective is to develop reliable models that somehow take into account not only these universal properties or not universal properties, but we have some control on, along with all the other complications related to that. This could be large eddy simulations, the renormalization group-based models, or it could be RANS, Reynolds number, Reynolds average, the equations, etc. The most challenging ones are this, and I want to spend a little time on how the problem has become complicated now than before. So in such a flow, everyone learns in the first course on turbulence. So basically, generations of people have learned this. That could be many thousands of people, many hundreds of thousands perhaps. And what do they learn? They learn that not too close to the wall and not too close to the boundary, the velocity distribution increases, the velocity increases with distance from the wall in a logarithmic fashion. This is a so-called log law. It has a great pedigree. There is the Millikan, the name of Millikan associated with that. And he constructed a singular perturbation theory that basically showed how the outer layer and the inner layer have to match somehow to give you this. So the pedigree is enormous, and this constant here, kappa, is supposed to be universal, whether it's a pipe flow or channel flow or any such flow on the wall. Now, this is the von Karman thing. So you see it has a great pedigree, as I said, and many people have studied this, taking it to be a constant. But of course, it turns out that it is not a constant, and it depends on the flow, for instance, and perhaps also to some degree on Reynolds number. Were all the others propagating falsehood? No, that's not the case. The thing is that you can measure things now better and better and greater accuracy, and therefore you begin to see all these small differences, and those small differences may have a very fundamental significance for the flow. So a disturbing conclusion is that this is not universal and depends particularly on pressure gradient much more strongly than previously thought. Previously, if you remember the paper, or something you may remember, Ludwig and Tillman, many years ago, basically it said, if it is zero pressure gradient, that's correct. If you go a little to the right or to the left, it will still be correct, but it is not. It's very strongly dependent on this. Now, this is something we are learning now. Now, the problem, of course, what always puzzled me was that in statistical systems like this, where fluctuations are very strong, somehow the fluctuations are the ones that affect the mean, right? That's what is happening, because the velocity profile for a laminar flow and a turbulent flow are very different. Therefore, somehow the fluctuations are affecting the mean. But none of the theories that I just described before, like the log law, recognizes this fact. There are no relation to the fluctuations themselves. So one has to study what the fluctuations are, but I get too technical on this, so perhaps I shouldn't address this. But the point is that you have to take the fluctuations into account, and they have a certain behavior with Reynolds number. There are two different theories. One goes logarithmic like that. The other one increases, and then it sort of saturates. We can't tell exactly from the available experiments. You need to go higher. And so we had this theory that said that it doesn't keep increasing indefinitely like a logarithm, but actually saturates. Okay, we don't know if this is true or not yet. Let's skip that. I want to come to engineering perspective on this. So people now can do wonderful things with these so-called closure models and computational fluid dynamics. They do not recognize anything that's happened in anomalous exponents, regularity of the equations, and things like that. They just happily go ahead and solve them on the computer using various closure models. Whereas the DNS people, that is the direct numerical simulations people, they don't have any model. They just solve the equations that they are. The problems there could be resolution is not enough. You don't have long enough records and things like that. But now we are in a position using the so-called DDES, which is just Reynolds average, Navier-Stokes, which Rishita works on here, for instance. LES, which Joseph works on here, for instance. So it's a combination of these things that will produce for you streamlines on an aircraft, or also a little bit on the vorticity, for instance. Of course, you don't know whether this is right or wrong in some fashion, because after all, there are models that include many unknowns in them. Nevertheless, you cannot escape the feeling that you ultimately have to do this, and somehow we should not forget while we do, let's say, regularity and anomalous exponents, the connection of those with what is happening here. The responsibility is on both sides, and not only the people who do the anomalous exponents, etc., but also those who these models. So now I have described to you a set of problems that I regard are very important and one should understand. And solving any one of them already advances the field a lot. If, of course, a few of them are solved, then we advance the field enormously. So can we say, when can we say, following the title, that we have solved the problem, so-called problem of turbulence? You can never solve all the problems. There are an infinite number of problems of turbulence. So you can't solve them all, except through computing. You cannot solve them all. But there are some basic problems which, when you have control on, you can declare that the problem is solved. Right? This is what quantum mechanics does, for instance. I have sort of described for you, since there is no one single problem that I could think of that say, yeah, solve this and you have everything, I can describe a few problems that should be relatable to each other, and that should give you an indication that the problem is finished in some ways. And I described a few, I grouped them into four groups. One of them is the mathematical type, such as the dissipative anomaly, the regularity, weak solutions of Euler, about which I didn't speak. It's just technical, and connections among all these. Relations coming from Kolmogorov, they're very vital modifications and all that. So that's one. Another group is these vital variations from here go on from this box to this. So this is intermittency, a theory of anomalies, anomalous scaling, and saturation of exponents, which I think is really important. When the exponents saturate, what it means is that over a very small distance, which is tiny, huge fluctuations can occur. I mean, this is the idea of intermittency, but these huge fluctuations are as large as possible. For example, you heat a flow, and let's say you heat it to 40 degrees centigrade, and fluctuations in temperature cannot exceed 40. But the general idea is of the saturation of exponents is that even over tiny distances, sometimes you see 40-degree variation in temperature. You can convert it to velocity if you want. So the third box is the effect of fluctuations on the mean, which really modifies things like log law and things of that sort, which have been held sacrosanct for many decades now. And there is a certain thing as the sociology of the field, about which I would like to make some remarks. The sociology of the field is very interesting because all of them have an effect on how the field evolves and the perception of people within the field and the perception of people outside the field. Sometimes you think you have made big progress within the field, but outside the field, yeah, okay, probably all right. And well, where do we stand? That actually makes a big difference to how the field is perceived from outside, how many prizes one gets. I'm not saying one should be hankering for prizes. The turbulence problem, this has certain sociology associated with that. And the sociology is that everyone has his or her own problem of turbulence. They have very pet problems. If you ask a certain group of people, they say, unless, let's say, you can figure out what the drag in a pipe flow is, or pressure out in a pipe flow, you haven't solved the problem. But if I solve this, this may not be enough, although it's very important. And if you ask somebody else, she might say, well, if you solve the problem of anomalous exponents, you have moved the field a lot. Indeed, it is true. But then, as I said, it may excite some people, but may not excite all the others. And the problem is there are just too many problems, and everybody has a certain pet problem. And generally what happens is if you have a huge group of people, let's say working on some method of closure, and this huge group has a social implication because they produce more graduate students, one after the other, and the field somehow just moves in a certain direction, and it is very hard to bring it back if you go like that. So that is one thing. And there is a false expectation that there is a turbulence, there is the turbulence problem, and if you solve it, you have solved it. If you haven't solved it, there's nothing really important is happening. That's not true. It really has many problems, and there are progress that one makes on all these fronts continually, and sometimes very strong progress, but others do not recognize that necessarily. And the other thing is that turbulence is very familiar to everybody. They say, well, if you want to measure humidity, you just lick your finger and put it like that, and you have an indication of humidity. That's perfectly true. But of course, if you want to measure it in a scientific way, it's a different problem. You really have to work hard at it. But if I just put my finger up and measure it, you can't say, yeah, I know how to measure turbulence. You cannot really say that. And that quite often happens because it's important enough and familiar enough. It's not like, let's say, high energy physics where you couldn't do anything unless you have a big accelerator. Otherwise, you can sit and roll your thumbs and prepare for the accelerator that may come 20 years down the road. I don't know which is better, but my point is that sometimes you have to take the trouble to do the right thing, measure the right thing, not just measure anything that's available to you and that you can do quite easily. So this, what it means to me is that it's very easy to obtain facts in turbulence. You can take a tank and put a dye and spur it and you can see mixing. There is nothing wrong with that. But to characterize it at a scientific level in order to make a theory, for instance, is much harder. And therefore there is this dynamics of sociology of turbulence, and the fact that many people think that there is one problem, a big grand problem, and okay, the solution is awaited, some messiah will come and solve this, and then we can say, well,
the statement that I attributed to Feynman is now no longer relevant. Well, that's not how it has been, and that's not how I believe it will not be. So there are many interesting problems. It's like a field in itself. Many interesting problems, some mathematical interest, some physics interest, some engineering interest. I decry the fact that the connection among them is not appreciated by a large number of community members in the community. And so they think the progress in one area, then just those are not their head and move on. But that's not how it is. It really is that progress in one area actually impacts everything else, and one will have to work harder in order to understand what others have done. So basically that is my summary for IU, the way I see the situation today. In a few years I might change my mind, but this is a good reflection on the situation. So I greatly appreciate the time you have given me and the patience with which you have listened to me. So thank you very much. I'm very happy that Rahul is giving me this.
Well, thanks everyone for coming for this lecture. I also wish to thank our Deputy Registrar, Veeran Nakabar, and his team in the PRS office, which put together all this lecture. In the Aero department, Mr. Suresh in the Space Technology Cell, and several others, as well as Dr. Duburi for their arrangements. Thank you very much. We have high tea in the room across.